All right, we are actually going to do two um, sections. Mass, section 5.3 is such a short, it's only one slide, and then Newton's second law. So we're going to combine those two. So let's get on with the slideshow, and we're going to talk about mass. Mass is a property that specifies how much resistance an object exhibits to changes in its velocity. Well, what is a change in velocity? A change in velocity is equal to is acceleration. So you can look at uh, there's a inverse here. The ratio of mass 1 over mass 2 is equal to the acceleration of a2 over a1. Mass is one of the indicators of mass is inertia. The more mass an object has, the more inertia it has. I'll give you an example. Let's say you're at a Home Depot or at a Lowe's, and you've got a brand new car. You park it far away where nobody's going to scratch it. And as you park your car, you see an empty basket, one of these little plastic baskets coming towards your brand new car. Do you panic? No. You get in front of the basket, and you stop it. Why? Because it's empty. It doesn't have much mass. It doesn't have much inertia. Now, let's say that uh, same basket, or you park your car, but you see a basket coming at you, but now it's full of concrete tiles. I mean, full of concrete tiles, and it's uh, coming fast. Do you get in front of it like the other one? Most likely not, because it's got a lot of inertia. There's a lot more mass, so there's a lot more inertia involved. It's just so that's inertia of moving objects. So let's say uh, after a while, your car gets dinged up, and now you're parking close. You're parking close to the entrance, but uh, you park your car. You come out, and when you come out, somebody has left an empty basket in front of your car, and you can't exit. Do you call management and say, hey, you need to move this basket? No, if it's empty, you just move it yourself. But let's say it's again, somebody left a basket full of um, concrete uh, bricks or pavers. You may have a hard time moving it. Why? It has more inertia. Empty basket, you just push and it'll go. Concrete pavers, you're going to have to really push. It has more mass. It has more inertia. Okay, so the acceleration is a lot less the more mass it has. Okay, let's and actually that's the end of 5.3. Now we're going to get on to Newton's second law. If you apply a force to a mass, the acceleration of the mass is proportional to the force. And it's the so if you apply more force, you get more acceleration. It's inversely proportional to the inversely proportional to the mass. Same force, you have you apply a force to a mass, you get an acceleration. You apply the same force to double the mass, and you're going to get half the acceleration. If you apply the same force to, if you cut the mass in half, if you apply the same force, you're going to get twice the acceleration. So it's inversely proportional. Acceleration is inversely proportional to the mass and directly proportional to the force. Okay, when viewed from an inertial reference frame, the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Okay, so the acceleration is that's the little squiggly line. That's the proportionality symbol. The acceleration is directly proportional to the net force and inversely proportional to the mass. Now, look at the. If you look here, um, acceleration is a vector, and even though here they're talking about the if you remove the absolute value symbols, that the absolute value symbols means the magnitude, um, but the acceleration is a vector, force is a vector. Now, if you recall way back from chapter 3, our discussion on vectors, here we have a multiplier. So it's the same vector, but it's multiplied by 1 over m. So what did you know? What do you remember about multiplying a vector by a scalar? All it does is change the size. It's in the same direction. So the acceleration is in the direction of the net force. So they're both going to be in the same direction. So it's the acceleration is in the direction of the net force. Now, there could be multiple forces acting, but the overall, as you learned in your vector table, there is a resultant. So it's the sum of the forces end up in some resultant. So the acceleration is is directly proportional to the resultant of all the forces acting upon it, and it's inversely proportional to the mass. Okay, let's. So here we were using the proportionality symbol. Here we're using an equal symbol. You could have just as easily used an equal symbol here. Acceleration is equal to the net force divided by mass. Now, if we divide both sides of this equation by the mass, we'll see that force, the sum of the forces, equals mass times acceleration. Remember this one. The sum of the forces equals mass times acceleration. And so the sum of the forces in the x equals mass times acceleration in the x direction. Sum of the forces in the y direction equals mass times the acceleration in the y direction. And the sum of the forces in the z direction equals the mass times the acceleration in the z direction. Okay. Now let's look at a quick quiz. An object experiences no acceleration. Which of the following cannot be true for the object? A single force acts on the object, no forces act on the object, or forces act on the object, but the forces cancel. Okay, so which one cannot be true? And the one that cannot be true is a single force acts on the object. If a single force acts on the object, there's going to be motion, because the sum of the forces, if there's no force to cancel it, you have a single force, you're going to have the sum of forces equals that single force, and you're going to get acceleration. So if there's no acceleration, that could be that no forces act on it, but most likely the forces are acting on the object, but they act in the opposite direction. Now, notice it says there's no acceleration. Did it say that there's no motion? Oh, you know what? I might be getting ahead of myself. Oh, there's the answer. Single force acts on the object. No, it doesn't look like it. The fact that it says an object experiences no acceleration, it doesn't mean that there's no movement. It can mean that there's no movement, like I spoke earlier about my computer, my laptop here on the table. There's a gravitational acceleration downward, and there's a normal force supporting the laptop from underneath. So those two forces cancel. There's no motion and there's no acceleration. But now let's look at someone like a skydiver that has jumped out of a plane in free fall. He's going to reach what is called terminal velocity, in which his velocity is going to not increase anymore. So is he moving? You bet he's moving. He's moving downward because of gravitational acceleration. But the drag force has caused him not to accelerate anymore. He's reached terminal velocity. So the downward gravitational force is counteracted by the drag force. And so he's not accelerating. It means he's going at a constant speed. So no acceleration can mean that it's not moving, but it doesn't necessarily mean it's not moving. It can be moving just at a constant velocity. Constant velocity means no acceleration. It means the sum of the forces is equal to 0. Okay, let's look at the next one. You push an object initially at rest. You push an object initially at rest across a frictionless floor with a constant force for a time interval delta t, resulting in a final speed of v for the object. You then repeat the experiment, but with a force that is twice as large. What time interval is now required to reach the same final speed v? Okay, and let's just give the answer. It's delta t over 2, because you're applying more force. You only have to apply it for a short period of time to get the same final speed. Okay, these are some of the units of force. Now, mass is measured in kilograms. Now, we often exchange or use words like force or kilograms and pounds interchangeably, but they're really not. If you wanted to exchange them, kilograms, the equivalent in the imperial units, or SI in imperial units, I'm going to call it, is slug. In pounds, the equivalent would be newtons. So 1 Newton equals 1 kilogram times 1 meter per second squared. So 1 kilogram meter per second squared is 1 Newton. The 1 pound is equal to 1 slug times 1 foot per second squared, I guess. I don't really use those units. Slug is a unit of mass, pounds is a unit of weight. So weight in the SI units is newtons. Okay, 1 Newton is about a 1/4 of a pound. I don't know that you'll need that, but there's the information. Okay, let's see. All right, and that's the end of that section. We're going to go on with Newton's second law.